hope you're all well fed. First up, this is the Creative Arts Miniconf, and first up we have Jussi giving a presentation about fonts and math. This is a talk that I think he volunteered for 2 days ago? One day ago, because our original speaker in this time slot unfortunately has taken ill and couldn't attend the conference at all. So over to you. Thank you.
Right. Good evening. Welcome. Some forewarnings, which you already might have heard, that I did find out doing this about 24 hours ago. I spent the entire weekend traveling from Finland to here. So I was on a plane where I didn't sleep much. And also the Wi-Fi was broken, so I couldn't do background research. So this presentation is hopefully going to be interesting, at least in some way. To you, perhaps not to me. Anyway, even more, I have actually never done font design in Anger, so a lot of it. I only just like debug it. Are there people here who have done font design? Oh, anyway, okay, some good. Okay, so if I get some of the terminology or like things that actual font designers do wrong, it's just because I don't know what they actually are. So, but please speak up if there's things wrong. So the way you do fonts, the basic approach is that you have an idea of the kind of thing that you want to do. And then you start a font forge or some other tools, and then you draw the letters one by one, where you have the outline, and then you draw it using Bezier curves. And then you do that for all the letters, so the 26 lowercase letters, the 26 uppercase letters, and then you have the accented versions and the numbers and all the special characters and so on. And it takes a fair bit of time. And then you keep improving that iteratively until you're satisfied with the result, and then you release that. This is a fairly straightforward approach to doing things, but there are some like severe downsides. One of the biggest things is that there's lots of manual work. In the olden days, when you had to do font hinting, that was even more tedious. But just doing all the outlines is a lot of work. And each letter is its own unique snowflake, so you have to do all the things in advance, and for that specific letter. And it's quite easy to get like little things wrong. When you draw all the letters, then you look and you say, okay, so this one appears to be a bit thicker than the other ones, so you now have to do and manually fix it so it looks the same as all the others. And now that I do this one actually looks a bit off and so on, and it takes a lot of work. If you want to do different weights for your fonts, you have to do this again for every single one of them, pretty much from scratch, because it's not easy to just say something. There are some techniques like multiple master fonts, which are an Adobe thing, I think, where you draw a very, very thin one and a very thick one version of the letter, and then you just, it somehow calculates the average between the two. And it's actually quite hard because they're like, if you have lots of letters, they have parts that repeat, but they are slightly different, like you have the bowls in the P and so on. And it's actually quite hard to make sure that they are all in the same way, like have the same ratio of width to height and the thicknesses and so on. And little errors like these keep cropping up. So are there other ways of doing fonts? And it turns out that there are. This is the original one, which is called Beta Font, which was created by Donald Knuth in 1977. I think it was May 1977, so it's the same time as the original Star Wars. And this predates all of the font systems in use today. And the landscape for computer fonts at the time was that there isn't a landscape, so people were doing some things, and they were like typesetter machines and so on. But there wasn't really like a general pool of knowledge to pull from. And the basic idea that he had was that you can draw computer fonts in the same way that you draw fonts using a pen and nib. So if you mimic the way a person would draw by hand, you can then create fonts like with this. And each letter consists of one or more strokes, and you are done with a specific kind of nib. which nib means the shape of the pen that you're using to draw. This comes from calligraphy as well, as a term. And then you define the properties of those strokes and the nibs mathematically, and not like a visual thing, but in specific mathematical terms. And then you can use that information to generate the actual letters. So in detail, it roughly looks like this. You have a stroke, and it says at the top of the stroke is at some height. And then at some point, some other point, it's somewhere in the thing, at this point, the stroke needs to be going at this angle. So 45 degrees down, usually like vertical or horizontal at specific points to get the shade that you want. And so on and so on. And you define all the things. And then what you get is a set of linear equations for how the outline has to look like. And then you solve that, and then you get a specific description of how the letter should work. And this, the first part is done by the human, and then you just hand it out to the machine solving system, which does all the actual work. Here's an example of how it would look like. So this is a typical part of the letter A done in a calligraphy style. So you start at the top one, then go at the bottom. And then the way you would define this letter is roughly that it the very leftmost thing of this stroke is at the vertical line. The highest point is at the horizontal line at the top. At the bottom, it hits the bottom line, and then at the end, it goes like this. And then what the system would do is that it would okay, so I would have to start from there, and then there would need to be some sort of stroke of some time to get down here, and then get this part. And then when you do this, if you define your graphics in this way, you get interesting things for free. For example, you can change the width of the letter and the stroke of the letter individually. So typically, if you have this thing, if you want to make it narrower, what happens is that the letter also gets thinner because everything just gets closer together. But if you do it like this, then you just move one of the constraints closer to the other one, and then the system will calculate, okay, so what would the stroke be like in this case, so that it still satisfies all the things that you require. So I'm going to show you an example of how that works. I have here a calligraphy simulator, which you can do at home. It consists of 2 pens, and you hold them like this. And now you have a nib. So if you do a letter like this, it would go something like this. But if you want to make it narrower, then what you can do is you would do something like this. And from here you can tell that the change going from wider to narrower one is not just squishing everything together, it's that the whole shape of the letter changes. Because it's defined by these points, and then when you just squish them together, and then the system solves a new one, then you get a different kind of result. And then you can do these fine-tunings, and you can change the width of the letter, but still have the same stroke. And if you want to make a bold version of that, you just separate the pens out more, and then you do the same stroke, and you get one that's thicker, but it's exactly the same width and height. So this is kind of nice. Right. Okay. And you can do things like you can do an italic version where you just slant the control points. Now, if you just do the slanting on a regular font, it gets even thinner and it looks really bad. But if you just do the tilting on the control points and then do the stroke again, you get again the same width, and you can fine-tune the angle at which your italic sloped by just changing one parameter, and it will recalculate everything. So then we have the next problem. So we can define these points, which are defined in terms of these restrictions. but you have it's called a skeleton, like the middle line of the stroke. So you need to, so how should it go from one point to another? What should it be like? And for this, I need a volunteer from the audience for a small drawing sample, and our chair has agreed to be the volunteer. So here,
I've been volunteered.
yes. So here we have a set of points: 1, 2, 3, 4, 5, and 6. And your task is to draw a line that starts from here, ends here, and goes through all the points, and in your view is aesthetic in some way.
And no rehearsal.
Right.
Do I pass?
Yes. All right. Thank you. So how many here would have drawn roughly the same thing? Okay, well, fairly. Okay. So what we can learn from this is that human beings consider like these soft, sloping curves pleasant to the eye, and if you have sharp edges or something like that, it's usually not. So what you want to do is that if you have some sort of mechanism, given that you have these points, to get a path that goes through them and looks pleasing to the eye, then you can use that as the basis of forming your fonts. And this is also in Metafont, and this was named by Donald Knuth as the most pleasing curve. And this is a mathematical description of given that we have these points, what would be the most pleasing curve that would go through them. But Donald Knuth was a mathematician, and then he has the way a mathematician works is okay, this probably doesn't exist. Like, you cannot say that any curve that you draw through these points would be the most pleasing across all people in the world. So it probably doesn't exist, and it in fact cannot exist. But if it did, what properties would it have? Like, this is mathematical thinking 101 here. This is pretty much the thing. And it seems a bit strange, but actually this kind of makes sense, because when you start actually going through the requirements and things about it, you find out things that you really didn't consider before. So he postulated a set of requirements that a most pleasing curve should fulfill if it exists. And the basic ones, okay, scale invariant, rotation invariant, translation invariant, mirror invariant probably as well. And derivatives of the function or the curve should be continuous up to some level. Some like maybe 2 second derivative, maybe third one. I don't actually know the actual number, but they should be continuous because that's how you get smooth curves. And this was an interesting observation. So if you have points, the considered points that are on a circle arc, then the most pleasing curve should be the circle that goes through those points. And this is again, a mathematician speaking. So if you have a most pleasing curve defined by some points, if you add one point to the set of points, which is on the curve itself, and then you recompute the most pleasing curve for those points, it should be identical to the one you did without the extra points. Because, yeah, it makes sense because there's no extra constraints there. But it turns out that these are impossible to satisfy all of them at the same time. The mathematical proofs of these are in Donald Knuth's papers. And much like the art of computer programming, I haven't actually read it, but I'm told that exists, and I'm completely happy with that. All of these are impossible to satisfy at the same time. So, do the things that you have. And then I think there were 2 or 3 PhD theses made out just on this problem alone, or related to text and Metafont. And the algorithm that they then came up with, and which is the one that Metafont uses, roughly goes like this. Take 3 consecutive points of the list of points that you have. And you fit a circle on 3 points, because that's given 3 points, you can always fit a circle on that, and the solution is unique. If they're a straight line segment, just let's pretend that they're not a straight line segment. And the most pleasing curve has the same direction and value in the middle point as the circle has that goes through it. So this is perhaps better looked at through an example. So we have 3 points, 3 of many. And then we fit a circle that goes through them. And then the point at the top, well, we know that at that point, the curve should have the same direction and the same curvature as the circle that's in that point. And then once you have that, you get rid of the circle, and then you get points and directions, which are constraints for the most pleasing curve that you want to draw. And then the actual task of drawing the graph from that is very complicated. Like the formulas are about this long, but this is roughly how it works if you look it up. In actual use, the only real font that ever was done with meta fonts in like proper fonts was Computer Modern. There were some minor other fonts, but they never took hold. And does everyone know here what Computer Modern is used for? Okay, so if you ever do a document with LaTeX or plain text, by default it uses the Computer Modern fonts. And if you ever read a document or a scientific article, then it's most likely written with tech, and it uses the meta fonts. And the font family is called Computer Modern. The interesting thing about it, which usually is not spoken of, is that Computer Modern does not behave in the way I just described. Because it turned out that the nib-based approach, or like the calligraphy-based approach, is not as flexible as you would imagine. So instead, what they do is that they parameterize the outline of the font, and then they fill that in, which is kind of similar to how regular fonts work. But the parameterization still stands. So absolutely everything about these fonts is parameterized. You have the X height and all the heights, stroke widths, the slants, and even the fact whether your character has serifs or not is a parameter, and you can set that. You can set the size of your serifs by changing the parameter. So if you actually look up the metafont files that you find on a regular Linux distribution, all of the letters are defined so that you have a letter C in some font, and then it just sets up a bunch of parameters with macros, and then it includes a different function which has the underlying letter C or letter S or whatever. So all letters of a certain type in a Computer Modern, across all of the Computer Modern families, come from the same function. It's just instantiated with different parameters. So here's an example. The letter M, both of these come from the same definition. It's just that the one on the left has a bigger number in the serifs, and it has parameters like do the rounding at when the two lines join and so on. And this actually, like, once you know this and you start looking at the letters, you can easily tell that this is the case. But if you don't know this, and it's just like they work together and they're kind of similar, but you don't know why. But now you know. Metafont never really took on because the Computer Modern family has 60 parameters, and you can change them. And you changed one of them, and then you run all of the generation things. And it's a batch processing system, basically. And then you get your results, and then it's like, well, now it looks different or not. And you really need to be a programmer to get the most out of it. And for this reason, it never really took on, which is kind of a pity. It would be kind of fun if someone were to try to do it again, maybe like a graphical user interface where you could have live updates and so on. So you could have a different kind of thing for font design, but for now it's not really used. Okay, but let's do an intermission. So here are the two thought puzzles. Suppose you have this. So you have a piece of metal, the bar here, that's affixed to a wall, and it has a weight hanging from the end. And at this, when it's like this, it's perfectly straight. So if you take away the weight, it will curl into some sort of other form. So what's the form that it's going to take once you cut a string? And if you prefer the differential equation solution version of the problem, and who among us doesn't, the same problem is that what is the shape of the curve whose curvature at every point is equal to the arc length up to that point, as you know. I'll let you think about it. Have a sip of water. Okay, I'm sure you all have the problem, so let's work it out. So let's go on the next one. Connecting railway tracks. This is an interesting challenge. So railway tracks consist basically of two parts. You have the straight segments where you go from one place to another, and then there are circular segments for turning the train around. But the thing is that you cannot have a straight line segment and a circular segment and just put them together, because what happens is that you have a discontinuity in the first derivative, and this causes wear and tear on the track, and also it causes like rough ride and feels unpleasant. So the problem then is that how should you join a straight line segment to a part of like an arc of a circle in the optimal way, so you have the very smooth experience. Now we assume that they're on the same height, which is called the elevation, and that you can ignore banking, which is called, and I kid you not, super elevation. But this is the problem. So how should you? And this was, I think, solved in the 1800s, or late 1800s. Well, and as I'm sure you all worked out in your heads, both of these problems have the same solution. It's exactly the same. And it's actually this one. So this is called the Euler, Euler. Oh, sorry, thank you. Euler spiral. So if they're in the middle, the point of symmetry is that's the origin, and then you go from there upwards. And if you were to cut the spiral at any point and have a weight attached at that point, then it would hang out completely straight. And if you wanted to join a circular thing, which with the straight line segment, so you put the straight line segment in the beginning, and then you find where the slope is the same as the circle, and it just catches that there. And this is the solution. This has been actually come up like tens of times, various times in different parts of maths for things. And this is it's kind of like a beautiful thing on its own as well. You could have like an art motif with anyway. This is the approach that was taken by Raph Levien. It's called the spiro. So if you have 2 points and the angle of the derivative at that point, then what you can do is that you form a path by finding a part of the Euler curve which fits those requirements, and then you just use that to join. And this is optimally smooth for some definition of optimality. And this turns out it has interesting properties which are interesting for the implementation. It's really fast to compute. You can get exact solutions out of that. And it's easy to have Beziers that do the same thing. So it's very easily approximatable with Beziers. And the resulting curves are very smooth and they're very pleasant. And this is available today, or has been for several years actually, in FontForge, and it's also available in Inkscape. And there's even a C library called libspiro, which you can use in your own applications. And if you want to know more about this, then Raph Levien has a PhD thesis where he goes through the design. And it's, as far as PhD thesis goes, it's really readable and it's really interesting. It's really well written, and I highly recommend it. And the last thing, what you can also do is that you can think of font design as a constraint, not only a constraint optimization problem. This is a thing that I did on my own. I wrote a blog post about it. You can go there for all the gory details. But the approach is again, fairly simple to explain, but the math gets a bit tricky. So you have a path, which is just Bezier segments one after the other. and you have the points, and you have the control points, and they are the free variables. And then you add constraints, such as direction constraints and smoothness constraints, and you can have constraints as like at this point, the distance between this control point and the defining point on this side has to be 3 times that on the other side, and so on and so on. And then you have a target function, which is something like smoothness or energy of the curve, arc length, whatever, what have you. And then you use numerical methods to minimize this. The results you get out of this are something like this. And when I say results, this is the only result that I have ever done. The letter S is actually the most difficult one to do because it's very difficult to get a pleasing thing out of it. But this kind of works. So the way this is done is that you have constraint points for at the top, so where the letter begins, and there's an angle constraint saying that it should go in that direction. And then at the top and at the bottom, you have horizontal requirements, and then at the points where it touches the sides, you have that it has to be vertical and at certain height. And then the optimization function for this is to minimize the maximum value of the second derivative, as one does, over the entire curve. And you can do that. So the status on this one is that it's mostly an interesting toy. I wrote it, and then I, at some point, got a bit bored with it. But you can run it in the browser with WASM, so you can type your constraints in the browser window and just press, and it will calculate it, the results. If people are interested, like the things that you could do is you could experiment with different objective functions, because if you have different constraint or objective function, the shape of the curve that you get out of it is different. So it would be interesting, like what would be a good function to get pleasing results out of it? Or maybe the function that you need to optimize is different on different letters, and so on. There are interesting numerical stability function problems with this. If you want to know more, come ask me afterwards, preferably after I've had a few beers. It hasn't really been touched since last summer when I made this. And I hadn't read Raph Levien's PhD thesis at the time. Then I did read it and realized that what I had the default function that I used is actually the same, and it's a numerical approximation of the spiro algorithm. It just runs 1,000 times slower. But you know, that's how experiments work. In conclusion, there are interesting math problems if you are in the font design and things, and have fun exploring them.